Hello and welcome to Data Science for Everyone. In today's video, we will be learning about exploratory data analysis in Python. Imagine we have a new dataset. How do we start analyzing it? What kind of questions can it help us answer? Before we can figure out how the data might be useful, we first need to understand what's actually in it. This is called Exploratory Data Analysis or EDA. EDA is the process of cleaning and examining data to uncover insights. These might include things like basic statistics, patterns, relationships between variables, and potential trends. It also helps us come up with ideas for further analysis or experiments. The results of EDA often guide our next steps, whether that means forming a hypothesis to test, preparing the data for machine learning model, or even deciding that the data isn't useful and starting over with a new dataset. In today's tutorial, we will be using data exploration and plotting libraries in Python to perform exploratory data analysis. In today's tutorial, we'll go through several key steps in exploratory data analysis. We'll start with data inspection, where we get a first look at the dataset to understand its structure and contents. Next is data validation, making sure our data is accurate, complete, and free of obvious errors. Then we move to data summarization, using statistics and visualizations to get a sense of distributions, trends, and relationships. We'll also look at handling missing data, discuss strategies like imputation or removal, depending on the context. Exploring categorical and numerical data comes next. We'll use appropriate tools and plots to understand each type. And finally, we'll address outliers, figuring out whether they are data entry errors or genuine extreme values and how to treat them. Let's start with how to get a first look at a dataset to understand its structure and contents. Let's get started by loading in a dataset and exploring it. We will be using the pandas library, that is an open source data analysis and manipulation tool built on top of Python. We're going to work with the dataset on penguins that is derived from the famous Palmer penguins dataset. The link to the dataset is in the description below. Now that we're the data file, we should first import pandas as PD. Since the dataset is a CSV file, we will use the read_CSV function to read it into a data frame, which we will call penguins. Once the data is loaded, we'll use the head function to take a quick look at the first few rows. This gives us a snapshot of the dataset so we can understand what kind of information we are working with. From the preview, we can see that the data includes columns for row ID, species, island, etc. for each penguin. This gives us a great starting point for our analysis. By default, head gives us 5 rows. We can change that using the n argument and set it to any number we like. Similar to the head function, there's another function called tail that gives us the last 5 rows. We can change that using the n argument as well. Pandas gives us a quick way to check for missing values and see the data types for each column all in one go, using the info method. When we run it on a dataset, we can see that there are no missing values, which is great. But we do notice that the columns have different data types, and that's something to keep in mind moving forward. A common question when working with categorical data is, how many data points fall into each category? Let's say we're looking at different penguin species in our dataset. To find out how many penguins are there for each species, we can simply select the species column and use the .valueCounts method from pandas. This gives us a breakdown of how many times each species appears. It is super useful for understanding the distribution of categories in our data. If we want a quick summary of the data in our numerical columns, pandas has a handy tool for that, the describe method. When we call the describe method on our data frame, it gives us key statistics for each numerical column, like the count, mean, standard deviation, and even the minimum, maximum, and quartile values. In our penguins dataset, this means that we get a summary for columns like bill length and body mass, helping us quickly understand the overall distribution of those numbers. Histograms are a classic way to understand the distribution of numerical data. They work by dividing the data into bins, which are ranges of values, and showing how many data points fall into each one. In this course, we'll use libraries called matplotlib and seaborn for data visualization. We import seaborn as SNS, and we'll also bring in matplotlib.pyplot as PLT to help display our plots. To create a histogram, we'll use the sns.histplot function. We pass in our penguins data frame using the data argument and then specify the column we want to plot, in this case bill length, using the x argument. We can also set the plot title, x and y-axis labels as well. Once we run plt.show, we can see the plot. Most of the penguins, as you can see from the histogram, have bill lengths of 45 millimeters, with a few above 55 millimeters. If we want more precision, we can reduce the bin size using the bin width argument. Keeping everything the same, I have set the bin width argument to 0.5 and we're able to visualize the distribution in more detail. Before diving too deep into our analysis, it is important to validate our data. This is a key early step in exploratory data analysis. We want to make sure that everything looks as expected. Are the data types correct? Are the values within reasonable ranges? Catching issues early can save us a lot of trouble later on. So with that in mind, let's dive in and take a closer look at our dataset. Before, we saw that the info method gives us a quick overview of a dataset, including the data types for each column and how many non-missing values are there. If you look closely, the year column is labeled as an object, but it needs to be an integer. How do we do that? Luckily, pandas make it easy to change the data types using the asType method. In our case, we can convert the year column to integer by selecting it and calling the asType method and placing int inside it. This tells pandas to store the values as whole numbers, which makes a lot more sense for the year data. After that, we can just double check by using the .dtypes attribute again, and sure enough, the year column is now correctly stored as integers. Here's a list of the common data types you'll see across all kinds of programming languages, along with their names in Python. When using the .asType method in pandas, it's the Python name that we need to use, like int, which we used to convert the year column type in the previous clip. Now let's look at how to validate categorical data. In pandas, we can use the isIn method to check whether the values in a column match a list of expected categories. You can apply isIn method to a single series or even to an entire data frame. Let's try on the sex column to see if all the values are either male or female. We pass those two strings as a list of strings to the isIn method. The result is a new series that's the same size as the original, but instead of penguin sex, it shows true or false, depending on whether each value is in our expected list. If the values don't match a category, it will be returned as false. We can also use the tilde operator at the beginning of the code to invert the true and false values. If we want to filter the data frame to include only the values that are on our list, we can use the isIn code we just wrote before, combined with Boolean indexing. Now let's validate numerical data. To do this, we can select and view only the numerical columns in a data frame by using the selectDtypes method and passing number as an argument. If we want to find out the range and mean of, let's say, the bill length of the penguins in our dataset, we can use the .min, .max, and .mean functions. To get a more detailed view of how the bill length values are distributed, we can use seaborn's boxplot function. The boxplot shows boundaries of each quartile in the bill length data along with any outliers. We're going to learn about boxplot later in the video. By adding the y argument set to species, we can look at the distribution of bill lengths of all three different penguin species. Looking at the plot on the right, we can see that the Adelie penguins have the shortest bills in the dataset. Now let's look at strategies of how to summarize the data into different types of statistical outputs. If you really like my videos, please like and subscribe to my channel. It gives me motivation to make more videos like this. Also, please don't forget to click the bell icon so that you don't miss any of my videos. To dive deeper into the characteristics of different groups within our data, we can use the group by method. This function lets us group our data based on a specific category, like species, and then apply an aggregation function such as mean or count to summarize each group. For example, if we group our penguins data frame by species column and then chain .mean, pandas will calculate the average of all numerical columns for each species. From the results, we can see that the Gentoo penguins have a higher average flipper length compared to other species, an interesting insight that might be worth exploring further. If we want to aggregate by a single feature, such as bill length, we can subset that column as demonstrated in the code. Other useful functions to chain with group by include sum, count, min, max, var for variance, and std for standard deviation. The ag function, short for aggregate, lets us apply one or more aggregation functions to our data. By default, it summarizes data across all rows in each column, and it is especially handy when you want to apply multiple functions at once. For example, we can call .ag on our penguins data frame and pass it in a list of functions like mean and standard deviation. This will return a new data frame showing both the average and the standard deviation for each numerical column. Note that the ag method only applies these functions to numeric columns automatically, so non-numeric data is ignored. We can take ag method a step further by passing in a dictionary to specify exactly which aggregation functions to apply to each column. In this dictionary, the keys are the column names, and the values are the list of aggregation functions you want to apply to those columns. This way, you have full control. For example, you might want to calculate the mean and standard deviation for one column, but only the sum for another column. The backslash, which is highlighted, is added just so we can continue writing code in the next line. By combining ag with group by, we can take our data exploration to the next level. For example, say we want the minimum, maximum, and mean for each of bill length, bill depth, and flipper length respectively. We can do this by passing a dictionary with named aggregations to ag. Each entry uses a tuple, where the first element is the column name and the second element is the aggregation function. The key we assign becomes the name of the resulting column in the output. This way we get clear labeled summary statistics all in one table. We can also visualize this kind of summary information using a bar plot. In Seaborn, bar plot automatically calculates the mean of the numerical variable, like flipper length, for each group in a categorical variable like species. Plus, they show a 95% confidence interval as a vertical line on top of each bar, giving us a sense of the variability in data. Here we pass species to the x-axis and flipper length to the y-axis. The plot confirms what we saw earlier. Gentoo penguins have the highest average flipper length compared to other species. Now let's illustrate how missing data impacts exploratory analysis. I have modified the penguin data by removing some data points for demonstration. The link to the modified data is in the description below. Like shown before, I have imported the modified penguins data using the pandas read_csv function. With our dataset stored as pandas data frame called penguins_mod, we can count the number of missing values per column by chaining the isNA and sum methods. IsNA identifies the missing values, which are represented as NA in data frames. The output shows that most columns contain some missing values, with body mass G missing the most, 64 data points. There are various approaches to handling missing data. One common rule of thumb is to remove observations if they make up 5% or less of the entire dataset. If there are more missing values, instead of dropping them, we can fill them with a summary statistic like mean, median, or mode, depending on the situation. This method is called imputation. Another option is to impute within subgroups. For example, if we notice that the body mass varies by species, we could fill in the missing body mass values differently for each species. Let's calculate the missing value threshold to see whether we need to remove or impute data for each column. To calculate our missing values threshold, we multiply the length of a data frame by 5%, which gives us an upper limit of 17 missing values. We can use Boolean indexing to filter for columns with missing values less than or equal to the threshold, storing them in a variable called calls below threshold. Printing calls below threshold shows 4 columns. We drop the missing values in these columns by calling dropNA, passing calls below threshold to the substring argument. We set in place equals to true so that the data frame is updated directly. Now let's learn how to impute missing values. First, we filter for the remaining columns with missing values using Boolean indexing. We see that there are 5 columns which still has missing values. To impute the mode for all 5 columns, we loop through them and use the fill_na method, passing in the mode for each column. We access the mode by indexing the first item with square brackets, since mode returns a series. Checking for missing values again, we see that no column have any more missing data. Let's say we want to impute the median for bill length by penguin species instead of the mode. We can achieve that by grouping using species and calculating the median. Then we convert the group data to a dictionary using the toDict method. We impute using the .fill_na method, providing the species column and then calling the .map method, inside which we pass the bill length dictionary. Now let's look at how to explore categorical data. To explore categorical data, we'll use a new dataset called salaries. I have imported the data using pandas readCSV function. In salaries data, there's a column containing the job titles for each employee. The name of this column is job_title. Let's take a look at how often each job title appears in this column. We can use the value counts method to see all the different job titles and how many times each appeared in the dataset. We can also find out how many unique job titles there are by using the pandas nUnique method. It turns out that there are 50 in total. We can use pandas string.contains method, which lets us search a column for a specific string or multiple strings. For example, if we want to find out which job titles include the word analyst, we apply the .string.contains method on the job title column, passing analyst as the argument. This will return true or false values based on whether each row contains the word analyst. If we want to filter rows containing one or more phrases, like job titles with either analyst or manager, we can use string.contains method again. This time we separate the two phrases with a pipe. The result will return true if a job title either contains analyst or manager, and false if neither phrase is present. Be sure not to add any spaces before or after the pipe, as this would restrict the search to only those titles that have a space before or after the phrase, which isn't necessary here. Once again, this will give us a series of Boolean values. If we want to filter job titles that start with a specific phrase like data, we can still use the string.contains method. This time we include the caret symbol at the beginning of the string, which tells pandas to look for matches at the start of the string. For example, caret data will match job titles like data scientist, but it won't match titles like big data engineer since big comes first. Likewise, adding a dollar symbol at the end tells pandas to look for matches at the end of the string. Now that we understand how this method works, let's define a list of job titles we want to search for. We'll start by creating a list with different categories of data roles, and this list will become the values for a new column in our data frame. Next, we need to create variables for our filters. For research roles, we'll look for titles containing data scientist or research scientist. For analyst roles, we'll use analyst or analytics. We'll repeat this process for other roles like engineer and manager. The next step is to create a list containing all the conditions for string.contains method. We'll use the conditions variable to save this list. We add the categories that we had defined earlier, which are research, analyst, engineer, and manager. Finally, we create a new column called category using numpy's select function. This function takes a list of conditions as the first argument, followed by a list of arrays to search for those conditions. We'll use the default argument to tell numpy to assign other to any value that doesn't match any conditions in our list. After printing, we see that a new column called category has been created. With our new column category, we can visualize how many jobs fall into each category. To do this, we use seaborn's count plot, passing our data frame to the data argument and category to the x argument. We then call plot.show to display the plot. From the plot, we can see that research, engineer, and analyst roles are by far the most common. After exploring categorical data, now it's time to move on to numerical data. First, let's explore the salary column that has salary in US dollars. We see that there are commas which makes this column non-numeric in nature. Let's make it numeric by removing the commas first. To remove commas, we can use the pandas string.replace method. First, we pass the character we want to remove, in this case a comma, followed by an empty string to replace it with nothing. After updating the column, we print the first 5 rows to confirm that the commas have been removed. However, the column is still not numeric. We can use the asType method, and inside we specify float to convert the salaries into decimal or floating point numbers. We can also apply mathematical functions on numeric columns and make new ones. For example, here I am converting US dollars to euros by multiplying the US salaries with the euro conversion factor of 0.88. We previously used pandas group by function to calculate summary statistics. In this case, we can chain group by and mean methods to find the mean salary in US dollars by company size. Let's say we want to create a new column containing the standard deviation of salary in USD with values conditional on the experience level column. The first step is to use group by, grouping by the experience level column. Next, we select salary in USD column and call pandas transform method. Inside the transform method, we apply a lambda function using the syntax lambda space x colon followed by x.standard deviation or std function. This will calculate the standard deviation of salaries based on different experience levels. Now let's look at how we can handle outliers in our data. So what are outliers? Outliers are those data points that stand out from the rest because they are significantly different. Let's look at this box plot to illustrate what outliers are. In this box plot, we're looking at employee salaries. We see that most people earn between $50,000 to $150,000 per annum. But there is one person who is earning $600,000. That is an outlier. If you calculate the average income without considering that outlier, the results get skewed, thus giving us a false impression that most people earn much more than they actually do. Outliers can result from errors in data entry, genuine variability in the population, or unusual but valid occurrences. In data science, we either investigate and explain them or remove them if they are not desired. So, identifying outliers is critical for making accurate, fair, and insightful data-driven decisions. We can define outlier mathematically. First, we need to understand the interquartile range or IQR. This is simply the difference between the 75th percentile and the 25th percentile. Once we have the IQR, we can identify these outliers. An upper outlier is any value greater than 75 percentile plus 1.5 times the IQR. A lower outlier is a value that is less than 25th percentile minus 1.5 times the IQR. We can calculate percentiles using the percentile method in NumPy. To find the 75th percentile of salary, we pass in 75. To get the 25th percentile, we pass in 25. Then we subtract the 2 to get IQR or interquartile range. When we print the result, we get an IQR of about $87,000. Now we can plug in these values into our formula to find out the threshold for outliers. First, the upper threshold, and then the lower threshold. When we print the results, we see that the lower threshold is actually below 0, which doesn't make sense since we are looking at salaries. We can use the boxplot function from seaborn to visualize the box plots. The empty circles represent the outliers in the dataset. We can remove the outliers by updating the code we use to filter the data. This time, keeping only the values greater than the lower limit and less than the upper limit. When we print the new descriptive statistics using describe method, we see that there are fewer entries. The mean salary is 5,000 lower than before, and the maximum salary has dropped significantly. To show the impact of removing outliers, let's start by plotting a histogram of the original dataset with the outliers included. The histogram is on the left. We can see that the distribution is right skewed because of high outliers. Now when we plot the no outliers dataset on the right, the salary distribution is less skewed and looks much closer to a normal distribution. With that, we have come to an end of our walkthrough on how to perform exploratory data analysis on unexplored datasets using pandas, numpy, matplotlib, and seaborn. If you like my videos, please subscribe to my channel. It gives me motivation to make more videos like this. Also, don't forget to click the bell icon so that you don't miss any of my videos. Please leave a comment on what topics you want me to make on this channel. Thank you and happy coding.